Hello, I'm Meral Kuyucu. I'll be presenting our paper on an authoring framework for creating IoT applications with mobile augmented reality that we called MARIoT. I'd like to begin by introducing myself. I graduated from Istanbul Technical University, ITU, in 2017. I continued my master's education at ITU with Assistant Professor Dr. Gökhan İnce on AR-enabled IoT. I graduated this semester. I will continue my PhD education at ITU, where I'm currently working as a teaching and research assistant in the Department of Computer Engineering. I intend to continue my studies in the field of human-computer interaction and AR-enabled IoT under the guidance of Dr. İnce. I'll continue with our study without further delay. With the launch of the Internet, components of the digital age, such as artificial intelligence, machine learning, augmented reality, and the Internet of Things took off. As described by Tid and colleagues, technology fusion can be empowering if the technologies fused are both cooperative and complementary. By fusing technology, it is possible to harness the advantages of both technologies and mitigate the weaknesses that arise from using these technologies individually. In this study, we propose the fusion of AR and IoT. We believe that AR can be a better suited method of visualization for IoT data because of the associated context awareness. IoT elements exist in 3D space, and an intuitive method of interaction is paramount. This is why the surface of interaction should also be in 3 dimensions, which can be achieved by means of context-aware AR. Thus, we propose mobile AR for IoT, or in short, MARIoT. This system consists of an IoT network, an AR authoring tool and application generator, and a communication server that lies between these two components. We aim to answer 2 research questions. First, will tech-savvy, but not necessarily code-savvy users find the suggested framework helpful when creating customized AR-enabled smart environments? And secondly, will users find an AR interface for interacting with IoT devices intuitive? There are many studies in literature that fuse AR and IoT. However, most of these studies lie in the implementation level. That is, no assessment of usability is made. One such example is the study conducted by Marquet et al. Studies which do conduct usability tests do so on prefabricated AR interfaces communicating with IoT devices. Although many studies focus on end-user development for AR and IoT separately, to our knowledge, there were no studies conducted on authoring tools for the integration of these 2 technologies. Let's continue with an overview of the MARIoT framework. The system consists of 3 major components. The first of these is a smart home IoT network. In this network, different types of sensors and devices can be connected to a microcontroller via GPIO, Bluetooth, or other means. A programming platform which runs on the microcontroller sends sensor information to a web server, the second component of the system, and listens to the server for user input commands sent to devices in the network. The third component of the system consists of a web-based authoring tool for creating augmented reality interface templates and a mobile application that can receive these templates via HTTP and generate them in real time. In the layered architecture of the system, the technologies that require programming knowledge lie at the bottom layer. Tech-savvy, but not necessarily code-savvy users can interact with these technologies using the abstractions we propose located in the middle layer to create customized applications at the top layer. We suggest 2 abstractions, namely the customizable task flow generator and the AR template generator. Let's look at these abstractions in more detail. The customizable task flow generator is a library containing task flows which users can import and customize without having to write code. The 2 flows in the library enable users to receive sensor information and send commands to devices. The data acquisition flow is triggered with the arrival of data. The sensor output is converted to a message that is meaningful to the user and sent to the server to be received by the AR user interface. The task realization flow, on the other hand, listens to the server for user commands. The flow is invoked when a user input occurs. The input is handled by the system and translated to a signal, which is then sent to the associated device. Here you can see a wireframe mockup of the template generator, a drag-and-drop web application with which users can design AR interfaces. Different types of UI elements can be dropped onto the canvas and customized in terms of appearance, content, data source, and marker image. Perhaps the most important component of the system is the publish-subscribe communication protocol. In this study, we chose the MQTT protocol because it is lightweight and suitable for IoT applications. All UI elements and IoT elements are clients to an MQTT server or broker. Some elements publish messages under topics, while others subscribe to topics and listen for messages. Now let's move on to the implementation of these system components. The dynamic AR UI generator was developed on the Unity game engine using Vuforia SDK. This mobile application is capable of taking a template of an AR UI and creating it dynamically at runtime. The AR template generator is a web application created with HTML, CSS, JavaScript, and the jQuery UI library. To create the customizable task flow generator, we adopted Node-RED, an existing flow-based visual programming platform for programming IoT devices. We created the library of customizable task flows on Node-RED. Lastly, we chose Mosquitto MQTT as the pub/sub broker. The hardware for the IoT network consists of devices, sensors, and a microcontroller. For the devices, we chose a desk lamp and a desk-sized fan. These devices, or actuators as we called them, were connected to relay switches. We chose to use a Raspberry Pi 3B Plus for the microcontroller. A microphone was utilized as a digital sound sensor, and a photoresistor was used as a digital light sensor. These particular sensors were chosen so that it would be easy for the user to observe ambient changes and visualize the related sensor outputs. The architecture of the pub/sub broker is as follows. On the left-hand side, we have the AR UI elements consisting of buttons to send user commands and text labels to visualize sensor readings. On the right-hand side, we have the sensors and the actuators. All of the elements are clients to the MQTT broker. The buttons publish user commands under some topic. In this case, the topic is device. A device is programmed to listen to messages sent under this particular topic, and when an on or off message is sent, this message is realized by the device. Sensors in the system act as publishers and publish the collected data under a particular topic. In the AR UI, a label is programmed to listen to the topic that the sensor publishes to. When new sensor data is published, the content of the label is updated in real time to contain this information. The customizable task flows were implemented in Node-RED. The data acquisition flow is triggered by a reading in the sensor node. The digital information is sent to both the date timestamp node and the handle node. The date time node creates a timestamp, and the handle node converts the digital message to a textual message understandable by the user. The timestamp and the textual message are combined in the join node and published to the server. The task realization flow is invoked when a subscriber node receives a message. This message is translated to a digital signal in the handle message node. Currently, the system supports on and off messages. The digital signal is then applied to the device. As mentioned, the AR Interface Generator application is a drag-and-drop web application that users can use to create AR templates. Currently, text labels can be utilized to visualize sensor information, and buttons can be used to send commands to devices. Each UI element can be customized after being dropped onto the canvas. A default MQTT IP and port address can be added before starting the template if all UI elements are to connect to the same server. This simplifies the cumbersome task of adding server information for each UI element individually. Now that you're familiar with the system, let's continue with the experimentation stage. The experiments were conducted at ITU User Experience Lab. Here you can see the experimental setup. Users program their IoT devices and create their AR templates using the computer. The sensors and the devices are on the desk. The two images on the desk are AR markers. These images enable context awareness. Each UI element will be binded with a marker image. An element will only become active on the AR UI when the marker image that it is binded to is in camera view. Before starting the tests, 2 pilot studies were conducted with expert users. The pilot results provided insight when determining the maximum time to complete the tasks. The experiment is incremental in nature, and it's important that users remain focused throughout. Thus, the test tasks were timed so that users do not get sidetracked or lose interest in the experiment. Additionally, minor visual changes were made to the template generator to ensure consistency. The participants ranged 18 to 26 in age and came from different engineering backgrounds. They had varying knowledge of programming. However, none of the participants had experience with any of the technologies used in this study. Additionally, we preferred participants who had experience and interest in AR, IoT, and smart home automation. 3 dimensions of usability, namely effectiveness, efficiency, and satisfaction, were taken into consideration when determining the evaluation criteria. For effectiveness, we measured the completion rate and the number of errors made by participants. Efficiency was measured in terms of the time taken to complete a task. All 3 of these metrics were measured with direct observation. Satisfaction was measured between tasks with an after-scenario questionnaire and at the end with a system usability scale. Participants evaluated the questionnaire statements on a 1 to 5 Likert scale. I'd like to continue first with an overview of the experimentation procedure, and then detail the stages of the experiment. We start by giving participants a general introduction to the system. Next, we ask participants to complete a demographic form and decide if the participant is suitable to join the experiment. Afterwards, a pre-training stage is conducted for both AR and IoT ends of the system. Then, a training stage is given for IoT only. The experiment starts after the completion of this stage. The objective of Task 1 is to configure the IoT system. This task consists of 2 subtasks. After completion, the participant is asked to evaluate with an after-scenario questionnaire. The second task is the configuration of the AR end of the system. This task consists of 3 subtasks, followed by an after-scenario questionnaire. Finally, the third task is the interaction with IoT devices using Mobile Augmented Reality. This task has 2 subtasks. Before wrapping up the experiment, we ask users to evaluate with a system usability scale. Let's continue with the pre-training and training stages. In the pre-training stage for IoT, users were shown video demonstrations of importing and configuring a data acquisition flow and a task realization flow. For AR, users were only given a verbal description of how UI elements should communicate with IoT elements. In IoT training, users were able to import and configure 2 flows for a device and a sensor. Users were given this training because Node-RED is a pre-existing platform adopted in this study. Therefore, the usability of Node-RED is out of the scope of this study. Users received no hands-on training for the augmented reality component of the system because our aim is to measure how intuitive they find the authoring tool and the mobile application. They saw these for the first time during the test. Let's move on to the test tasks. The objective of the first task is to configure a basic IoT network of devices and sensors. The first subtask is to import a data acquisition flow and to customize it for a sensor. The second subtask is to import a task realization flow and to configure it for a device. In the data acquisition flow, users had to configure 3 nodes. First, the sensor node is edited so that the microcontroller pin to which the sensor is connected is selected from the set of radio buttons. Then, the digital output of the sensor is converted to a text message. In the case of a light sensor, the 0 output can be converted to light on, and a 1 output can be converted to light off for an active negative photoresistor. Finally, server credentials and topic to publish messages under are added to the publish node. In the second subtask, the sensor information and a topic to listen to are inserted into the subscribe node. The handle node is not modified by the users as it only accepts on and off values currently. Finally, the microcontroller pin to which the device is connected to is selected from the set of radio buttons in the device node. The objective of the second task is to use a template generator to design an AR interface. This task consists of 3 subtasks. The first is to enter the default server information. The second is to add and customize labels to listen for sensor data. And the third is to add buttons to send commands to the devices. Here you can see a demo of the first subtask. After setting a default IP and port, the user does not have to repeat this procedure for each UI element. Let's move on to a video demo of the second subtask. Here, a label is added to the canvas. Some placeholder text is written for content. The topic to which it should listen to is added. And finally, a marker image is uploaded. This is repeated for the sound sensor, but with a different marker image. In the third subtask, the user should add 2 sets of on-off buttons and configure one to send messages to the fan and the other to send messages to the light. The content is the message that will be sent, so it should be either on or off. The topic should be the same as the topics given to the devices in task 1. The final task is to use the automatically generated AR interface to interact with sensors and devices. There are 2 subtasks here. The first is to visualize sensor data, and the second is to control a device using the buttons. Here is a demo video of task 3. First, the lights are turned off so that a sensor reading is triggered. By holding the device towards the marker for the photoresistor, the user can see that the photoresistor has a different output. Next, the user is asked to use the GUI buttons to turn on the light. Afterward, the user is left to explore different markers. Users are also able to go back to the template generator to modify their template designs. Let's continue with experimental results. The task completion rate is high across all tasks except for the task of adding labels to the template, which is slightly lower. The average error per user is below 1 for all tasks. The average completion time for each task is significantly lower than the allotted time for all tasks except for task 2.2, which remains slightly higher. The after-scenario questionnaire results are 4.82 and 4.74 out of 5 for tasks 1 and 2 respectively. Finally, the system usability scale result is an 81.9, or an A. In addition to the numerical results, it's important to consider participant feedback. Most participants showed interest in the system. They inquired about using the system in their own homes and workplaces. Some participants stated that they felt accomplished after using the system. They also mentioned that the system was quite intuitive. In fact, one of the participants, who was a genetics engineer, mentioned that the concept of pups-up messaging was very close to a biological process. Some participants suggested different usage scenarios for the system. Lastly, participants gave feedback on how to improve the system. Another important angle to consider is the backgrounds of the participants. While none of the users were familiar with the technologies used in the system, some were computer engineers or computer engineering candidates with varying levels of programming knowledge. Others had no experience with programming. We split the participants into 2 groups, namely computer engineers and non-computer engineers, to analyze the difference in their performance. It was surprising to see that while some tasks were dominated by computer engineers, others were dominated by non-computer engineers. For example, computer engineers have a higher completion rate for task 1.1, but non-computer engineers have a higher performance in task 1.2. There was an insignificant difference between the 2 groups, even when one group dominated. From here, it can be concluded that the system is in fact usable by people who do not necessarily have programming expertise. To sum up, there are 3 main contributions of this study. First, an end-to-end framework integrating AR and IoT using open-source technologies is presented. Second, a low-code, no-code framework which provides users with the necessary abstractions so that they can create a personalized smart home application is established. Third, the usability of the framework has been tested using an application generated with this framework. In the future, we aim to incorporate different methods of data visualization, such as graphs. We will integrate different methods of context awareness that users can choose from. Numerous devices for AR will be supported, for example, head-mounted gear. Lastly, the cognitive overload with choosing a topic in Node-RED and then using that same topic in the template generator can be difficult for users, especially elder users. Enabling seamless communication between Node-RED and the template generator will reduce this cognitive overload. For example, instead of having to remember each topic, users can select active Node-RED topics from a drop-down box in the template generator. Thank you for listening to me. If you have any questions, please feel free to get in touch via email.